Atomic theory and atomic structure, that is going to be the topic of interest here in this lesson. This is the third chapter in my high school chemistry playlist on atoms, molecules, and ions. We'll follow up this lesson with an introduction to the periodic table, and then finish this chapter off with nomenclature, which is just a fancy way of saying naming compounds. Now, this is my brand new high school chemistry playlist. I'll be releasing these lessons weekly throughout the 2020-21 school year. So if you don't want to miss one, subscribe to the channel, click the bell notifications. You'll be notified every time I put one of these up. So atomic theory is the first thing I'm going to tackle here. And atomic theory went through several iterations to kind of get where it was. So sometimes you hear people talk about modern atomic theory because some of the earlier things had slightly different views and stuff like that. It kind of went through a process to get where it is. And John Dalton is responsible for pioneering this. He's one of the big people in history you're going to want to know for this chapter. So, but there are really four tenets to modern atomic theory, and you kind of got to know them all. And the first part is just that all of matter is composed of these little atoms. That's the first part. So, cool. Second part deals with elements on the periodic table, and that all of the atoms of an element are the same, and then all of the atoms of all the other elements then are different than the one you're looking at. So that if you look at all the different elements on the periodic table, that's the number of different types of atoms that exist. So carbon atoms are the same as other carbon atoms, but carbon atoms are different than oxygen atoms, essentially. Now, third tenet of atomic theory says that you can't convert the atoms of one element into atoms of a different type of element, at least not by normal chemical reactions. So it turns out there are nuclear decay processes like nuclear radiation, so where some of this does actually happen. But by normal chemical means, it's not possible. There used to be alchemists back several hundred years who used to try and convert lead into gold and things of this sort. And by normal chemical means, it was never going to happen. All right, finally, the fourth tenet of atomic theory is that the atoms of the different elements are going to combine in different whole number ratios to form compounds. That's where compounds come from. So if we look at like the formula for water, water is H2O. So, and what this means is that, so to form water, you're going to take 2 hydrogen atoms for every 1 oxygen atom. So whether you have a small sample of water or a big sample of water, if you actually split apart all the atoms and counted them up, you would have twice as many hydrogen atoms as oxygen atoms. They mix in a 2-to-1 ratio. Cool, so that's atomic theory, and as we said before, this again was pioneered by John Dalton, and I don't care if you really know their first names, but probably there are 4 guys really, and possibly a 5th, but we'll go with 4. Names you should probably know for the history, kind of pioneering atomic structure here. So, and John Dalton's the first, and you should just know that, yep, he's kind of like the father of modern atomic theory. He pioneered atomic theory, came up with his version of atomic theory. Good to know for him. So, next guy on the list is Thompson. That's J.J. Thompson, and J.J. Thompson discovered the electron, and it turns out he discovered what's called a cathode tube, which is just a beam of electrons, and they made these cathode rays long before they ever knew they were actually a beam of electrons. So, but he found out they were a beam of charged particles, so, and things of this sort, but he found out the mass to charge ratio of electrons, but he didn't know the mass or the charge individually, just that ratio. So, but he's credited largely with discovering the electrons. That's what you'd kind of take away with J.J. Thompson's name. Robert Millikan is the next on the list, and Millikan took Thompson's work a step further, and he actually figured out the charge on an electron, and he's got his famous, we called it the oil drop experiment. All he did was take some small little micro droplets of oil, and he charged them with electrons, and what he found is that every single one of these droplets had a multiple of a certain charge, and he figured, well, that smallest charge, these are all multiples of that are on these little droplets, that must be the fundamental charge, and it turns out that's the charge of an electron. So it is the smallest, unit of charge that's possible, and when something's, either positively or negatively charged, it is always a multiple of the charge on an electron. So, and because Thompson had already figured out the mass to charge ratio, once he figured out the actual charge on an electron, he was then able to use Thompson's ratio and figure out the mass of an electron as well. So, but take that with you, that Millikan figured out, therefore, both the charge and then by default or indirectly the mass of an electron. And then finally, Rutherford's the next guy. And Rutherford took a thin, super thin piece of gold foil, and he shined alpha particles, which is a form of nuclear radiation, at this gold foil. So, and when he shined the alpha particles at this gold foil, interesting thing enough is most of them just passed right through. So, and this was, you know, kind of a unique discovery, but every once in a while, some of them would get scattered in different directions or even bounce back in some cases. And so what he presumed then is that this gold foil was made up of mostly empty space. So with then concentrated areas of both mass and charge. And we now know that those concentrated areas of mass and charge are the nucleus of an atom. And so, but big thing you should know is that Ernest Rutherford discovered the nucleus with his shining alpha particles through thin gold foil. So that's kind of the basis. These four guys, you should know their last name and associate them just a little bit with what they did. So I kind of tried to give you the bare minimum on the study guide there. Cool. Now, I gave you also a little model of the atom there. So, because we want to talk about the structure of an atom. So now that we know that all of matter is made of atoms, now we want to talk about what's the atom made of. Well, there's really three what we call subatomic particles, and subatomic meaning smaller than the atom. So, and that's the proton, the neutron, and the electron. So, well, let's take a look at these for a second. So we've got the proton, which we symbolize with the letter P, the neutron with the letter N, and then the electron with the letter E. And oftentimes we'll put a little E negative on it. So it turns out that two of these particles are charged. So it turns out that protons are positively charged, electrons are negatively charged, and they're attracted to each other. So, and then neutrons are neutral, they have no charge, which is, you know, the source of all sorts of stupid jokes out there, right? You know, a neutron walks into the bar, orders a drink, says, "How much will it be?" And the bartender says, "For you, no charge." Yeah, it's terrible. So I told you in the first lesson that it wouldn't be the last lame joke you heard, and now I'm making good on that. All right. So if we take a look at the protons, neutrons, and electrons and what's really going on inside of an atom, so at the center of an atom, so this is where you get protons and neutrons. This is your nucleus. And then going around this nucleus are going to be some electrons. So, and we call it an electron cloud, and they're just kind of moving around and stuff like this. And so the protons are positive, so, and then therefore these electrons, they stay associated with the atom just based on the attraction to the protons in the nucleus. So they're attracted to the nucleus, just that plus minus attraction. Cool. Now it turns out that protons and neutrons roughly weigh about the same amount. And if we tried to weigh that in like grams or kilograms, it would be a ridiculously tiny number because these are really, really small. So what they did is invented a whole new unit. They called it the atomic mass unit, or AMU for an abbreviation, just specifically for talking about this stuff. It's kind of like saying, "Hey, Chad, how many miles tall are you?" Well, that's not really a convenient unit to get my height. So, but if you said, "Hey, Chad, how many inches tall are you?" We could go there. We could go like 68. So things of this sort. So it's just picking a more convenient unit to talk about the mass of these guys, because if we talked about the mass in grams, it'd be like, you know, 1.67 times 10 to the negative 24 grams, or 10 to the negative 27 kilograms, or it'd be stupid, you know, small numbers. So what they said, we'll just make this easy. Roughly 1 AMU for the proton, roughly 1 AMU for the neutron. So, but it turns out if you're really 1/1822nd of an AMU for an electron. So a super small fraction here. So electrons are far tinier than the protons and neutrons. And so as a result then, almost all of the mass of an atom is concentrated in that nucleus right at the center, with these little teeny tiny electrons floating around there. And I just kind of give you some scope here, some scale here. So think about this. This is 1/1822nd. It's weight for the electron of the proton or neutron. This is kind of like comparing a small car to a baseball. These electrons are way tinier than the protons and neutrons. And here's where things are going to get a little crazy and mind-boggling. If you kind of look at, you know, how big the nucleus is compared to how big the whole atom is, that's where you're going to see that the scale drawing in your study guide there is way off. So if you say, let's say we had the nucleus here, which again is super tiny, but let's just say we had it and we built a scale model and we used a marble for the nucleus, just a regular standard marble. So what you'd find is that the electron cloud around that nucleus would probably be about ½ a mile in diameter. So a little marble nucleus where almost all the mass is concentrated in the atom, and then ½ a mile for the electron cloud with these super teeny tiny electrons going around. So pretty crazy. And so this kind of goes hand in hand with what Rutherford discovered, is that, you know, most of an atom is made of empty space. And you know, every once in a blue moon, you'll get some concentrated mass and charge when you hit that nucleus, but most of an atom is made of empty space. Now, this is kind of mind-boggling because, you know, things feel solid, you know, but they're not. They're made of mostly empty space. So think about this for a second. If you leave the Earth's atmosphere and go out into space, now they call it space because it's mostly empty space. Now the truth is, even in empty space, it's not completely empty. Every once in a blue moon, you're going to like bump into a hydrogen atom, but not very often. So it's almost completely empty space. But then even when you come, you know, to the surface of the Earth and you start touching matter and stuff like that, even that matter is made of mostly empty space. Most of the universe, whether you're out in space or on a planet, is made of mostly empty space. It is mind-boggling. So if I asked you, what is most of this, you know, what is most of the stuff in between my ears made up of? You should say empty space. That's right. Cool. So most of the universe is made of empty space, which you just learned. All right. So, cool. So now we know what a nucleus is made up of. We want to move on to talking about isotope symbols, and we're going to specifically look at oxygen here. So an oxygen 16, 8. We'll put a -2 up there. We'll get rid of these guys. All right. So all those protons, neutrons, electrons, we need to account for them. And this is called an isotope symbol right here. And specifically, the O here stands for oxygen. So we got a whole bunch of symbols on the periodic table, and we're going to do a little more formal introduction to the periodic table in a minute. But O stands for oxygen. So most of the time, teachers are not going to make you memorize all of the elements of the periodic table, but it does on occasion happen. So, however, I will let you know, in college, it almost never happens. So, because we know that you're going to have the internet and you're going to have a periodic table on you at all times, you know, you'll have a periodic table on your sock in some cases. I've seen skirts, I've seen shoes, I've seen ties, I've seen tattoos. It's crazy. There's periodic tables everywhere. It's on the front cover of your book. You know, so it's on the wall in every chemistry room at most universities. So you're always going to have access to a periodic table, and so memorizing, you know, the entire periodic table is pretty much a waste of time, but it is a requirement on students every once in a while, and if that's the case for you in your class, I apologize. So, but what I do recommend is this. Probably just memorize the first 30. And when I say memorize the first 30, I don't even memorize like their atomic numbers or anything like that. I just want you to know that Zn stands for zinc. Know what the symbol, what element it actually stands for. So O is for oxygen, F is for fluorine, B is for boron, that kind of thing, up to the first 30, just so you can work with them. And most of the time, it's not so bad, right? C is for carbon. Usually the letter corresponds to the element, right? So there's a couple exceptions, right? You know, you go to Fe right here, and Fe is iron. So, and it turns out they use the Latin root fer, so for that instead. And for some of these, they end up using a Latin root. I apologize. So those would be a little more challenging, but most of the time, knowing that Zn is zinc, not so bad. Knowing that Ni is nickel, again, kind of makes sense. But cool. Associate the names with the symbols for at least the first 30. And the rest you need to know, you'll kind of get familiarized as you go through the process. So, but highly recommend there. All right, so if we take a look at this isotope symbol, so we call this bottom number here the atomic number. And it always gives you the number of protons every single time. So when I see this, I know that we've got 8 protons. Now the truth is this though, they don't actually have to give you the atomic number. They can erase it, and there you go. So the idea is that if you look, the entire periodic table is organized by atomic number, and oxygen, by definition, that's the number in blue here, is atomic number 8. So the number of protons determines what elements you have. So however many protons are in the nucleus, that is going to identify the element for you. So if it's 8 protons in the nucleus, that's oxygen, period, done. And so in this case, because oxygen is atomic number 8, is associated with having 8 protons, it doesn't actually have to be given here. So, but I put it on there just so we could actually talk about it. So, but that's the one number they can leave off of an isotope symbol. Now the top one here, we call the mass number. So, and that mass number is kind of like a rounded whole number. And if you recall, I erased it, protons weigh about 1 AMU, neutrons weigh about 1 AMU, and electrons weigh a super duper 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 tiny fraction of an AMU. And so what you really get here with this mass number, since protons and neutrons each weigh 1 AMU, this really, and the electrons weigh almost 0, not exactly 0, but almost 0, So this number really just gets you the total number of protons plus neutrons. And so in this case, oxygen 16 here. So that mass number corresponds to having 16 total protons and neutrons combined. Well, if the atomic number already gave us the fact that we have 8 protons, then the remainder must all be neutrons, up to 16 total. And so that's going to tell us that we must have 8 neutrons as well. Cool. So finally, off on the other side here, we've got the charge. So, and it turns out that atoms can often lose and or gain electrons from the electron cloud. So they typically aren't going to lose or gain protons or neutrons from the nucleus, at least not by normal chemical means, but they can lose or gain electrons from the electron cloud. And so when you see that you've got a negative charge here, that means you've got 2 more negative charges than positive charges. So in this case, with oxygen having 8 protons, which are positively charged, to have a -2 charge, there must be 2 additional electrons associated with this atom. And so in this case, we can figure out that we've got 10 electrons with this oxygen ion. Now, one thing to note, when we have an atom with no overall charge, it must be because the protons and electrons are exactly the same number. So if this didn't actually have a charge listed there, if it was just blank, that would imply that for the 8 protons in oxygen, you also would have 8 electrons, not like the one we've got here. And when you've got a neutral species, that's when we call it a neutral atom. But the moment you get a charged species, rather than calling it a charged atom, which is kind of technically true, but not the system of naming things we use, not the definitions we use, in this case, we call this an ion. So neutral atoms are neutral atoms or atoms, but charged species we call ions. So first little piece of vocabulary here. Cool. A couple other things you should know. So it turns out this is the most common version of oxygen, but it's not the only one. So there's another one out there that exists, so called oxygen 18. And in this case, it's got a mass number of 18. And the reason it's got a mass number of 18 must be because, well, let's work it out. In this case, because it's oxygen, it still has an atomic number of 8, even if it's not listed, and must have 8 protons. But with a mass number of 18 now, that means, again, this is protons and neutrons combined, and there's 8 protons, so there must be 10 neutrons. Cool. So it turns out that there are different versions of the same element, some heavier, some lighter. So with a heavier mass number, lighter mass number, and we call these different, thinking of the definition as I write this, isotopes. So iso means the same, but you get different types of the same element. So, and it's just because there's a different number of neutrons leading to a different mass number. That's what isotopes are. They're different types of the same element, different mass due to a different number of neutrons in the nucleus. Okay, last topic in this lesson, we've got to talk about atomic weight, also called atomic mass. All right, so if you look at a typical periodic table here, so we've talked about having an atomic number above. They're the same atomic number we saw in the isotope symbol I just erased. But what you also have down below is an atomic mass or atomic weight. So if, like for oxygen here, it's 15.9994. So you get a nice little decimal number and stuff like this. And for carbon, it's 12.011, things of this sort. So what's weird is students don't often get this, is that these numbers here, these atomic masses or atomic weights, are averages. So we just saw that there are different isotopes of oxygen that actually exist. So it turns out one of the common ones was oxygen 16, and then probably the next most common would be oxygen 18. So, but it turns out there's not a whole lot of oxygen 18 out there in natural abundance. And that's why when you take the average, it comes out almost exactly to 16, because pretty close to 100% of the naturally occurring oxygen atoms weigh 16. And so when you take the average, it comes out really close to 16. Same thing with carbon. So 98.9% of naturally occurring carbon atoms weigh 12. And so when you take the average of all of them, it comes out really close to 12. And for most elements, this is how it works. Most of them have one major isotope, and when you take an average of all the weights of all the naturally occurring isotopes, it comes really close to one whole number, because that's most of it. But there's a couple elements where that's totally not the case. And one of them here is chlorine. So if you look on your handout there, I gave you a table. There are two major isotopes for chlorine, not just one. And there's chlorine 35 and chlorine 37. So, and I put their exact masses to 2 decimal places anyways. So 34.97 AMUs versus 36.97 AMUs. And then I also gave their natural abundances. So here it's roughly a 3-to-1 ratio, so roughly 75% to 25%. But if we give it exactly, let's go 75.8% versus 24.2%. Now it turns out there's trace amounts of chlorine 36 that exist, but when I say trace amounts, I mean like 0.00000000000 something percent. It's super tiny that we can pretty much for all practical purposes ignore it. But for chlorine 35 and 37, we've got a fair amount of both. Now I can see that we have significantly more chlorine 35 though, and so with 75% and close to 76%, and when we take the average here then, the average should come out closer to 35 than it should to 37. And that's what we see on the periodic table. It's 35.4527. So a lot of periodic tables you'll see rounded to 2 decimal places and just say 35.45. Cool. A lot of students look at something like that and they're like, so I know it's got 17 protons because the atomic number 17. So does it have like 18.5 neutrons or something? Well, you can't have half a neutron. It doesn't work that way. And the key is that this number isn't the same thing as a mass number that we saw on the isotope symbols. That isotope symbol, that mass number was a specific mass for a specific isotope, whereas this number right here is the average mass for all the naturally occurring isotopes. Cool, and you've got another process for how we calculate these based on giving just this kind of information. So, and we're going to do what's called a weighted average. And you're going to take the percentage here and turn that into its decimal form. And notice 75.8% means 75.8 over 100, which means move the decimal back 2 places here. So we'll have 0.758. And you'll multiply that by the corresponding mass of that isotope. So multiply that by 34.97. Cool. We'll do the same thing with the other isotope. So we've got 24.2% means per 100, so 24.2 over 100, which again just means move the decimal back 2 places. So that's 0.242 times its corresponding mass, 36.97. Cool. And then you'll just add them together, and that will get you this weighted average. And let me pull out my trusty calculator here. All right, so 0.758 times 34.97 plus 0.242 times 36.97, and we get 35.454. And if we look, 35.454 is pretty close. So now I rounded these to 2 decimal places and I rounded these to 1 decimal place on the percents, and had I not rounded them, we would have got even closer to this number you see published on the periodic table. Cool, but big takeaway here again. So 1, the process for just calculating these atomic masses. And again, when we say atomic weight or atomic mass, that already implies an average of the naturally occurring isotopes. Cool, and that's what's published on the periodic table here. Cool, that sums up this lesson on atomic theory and atomic structure in a chapter on atoms, molecules, and ions. So if you feel like you got something out of this lesson, please consider giving me a like and a share. One of the best things you can do to support this channel. And if you're looking for practice materials or the study guides that go with these, check out my premium course on chadsprep.com.